In this video, we're going to look at some examples of related rates. So a related rate is when two or more quantities are changing with respect to time in some scenario. When calculating these, I would need to remember that time is our actual input variable that changes the situation. So we're going to have to do a kind of chain rule, quote unquote, every single time we take these derivatives. All right, so here's our first example. We have a rectangle that's expanding, causes length and width to change over time. So we have this rectangle. It might start like this, and then it expands out as it grows, and then it's like that. All right, so this rectangle is kind of expanding out, and the length and width are going to change because of that. I find an equation that relates to how the perimeter is changing over time. So right away, we need a formula for perimeter. So let's call this the width and this the height of the rectangle. We know perimeter is 2w plus 2h. All right, so now we can take the derivative of this perimeter equation, and we're going to figure out how all of it's changing. So the derivative of p is just 1, but it's not time. We're taking everything with respect to time, so we're going to get dp dt. So this is the change in my perimeter over the time. And then derivative 2w is 2, and the derivative of w is, with respect to t, is dwt. So this is how the width is changing with respect to time, and this is how the height is changing with respect to time. All right, so you can see, basically you're just taking your normal derivatives. It's just every time you have a variable, you can put a dw, dt, dht, and this just represents the change in that quantity over time. So the change in the width over time, the change in the height over time. In this example, we have the exact same scenario, but the only difference is now we're talking about how's the area changing. So the area of the rectangle is going to be width times height. So now when we go to take the derivative and figure out how things are changing, we're going to have dA dt. That's not any different than we had last time. So this is the change in the area over time. But we have w times h. So you have to remember, whenever we have multiplication, we're going to do the product rule. So we keep w the same. The derivative of h with respect to time is dh dt. Plus, now we keep h the same. The derivative of w with respect to time is dw dt. Right, so now we could start plugging in quantities and stuff like that. If we could figure out how the height's changing, how the width's changing, what is the width, what is the height, all that stuff, we could figure out exactly how the area is changing with respect to time. All right, but this is just kind of a thing to remember. All right, these are going to come up a lot in these related rate problems, and also remember your derivative rules. All right, so here's one where you actually kind of have some numbers involved and you're trying to figure out the situation at a specific time. All right, so the length of a rectangle is increasing by 4 centimeters per second. So let's say we have this rectangle. We have length and width. And so over time, this side here is going to kind of get longer, and my width is decreasing by 3. So my width is kind of going down. So after some time, my rectangle might look like this. All right, it's gotten longer, but kind of shorter. How fast is the perimeter changing when the length is 10 centimeters and the width is 5 centimeters? All right, so we know we have perimeter. Perimeter is 2L plus 2W. All right, one thing that you don't want to do in these related rate problems is plug in these numbers right now. I don't want to plug in 10 for length and 5 for W because that kind of forces them to be the same for the entire problem, but they're changing. We're just trying to look at one single snapshot. So what we're going to do now is take the derivative, which we've pretty much done before. It's going to look like this. And we're trying to figure out how is the perimeter changing. The perimeter is changing by the 2 is just going to stay. At the change in the length over time, we know the length is changing by 4 centimeters per second, so that's going to be a 4. And the change in the width per time, that's decreasing by 3 centimeters per second, so that's going to be a negative 3. Remember, a decreasing change is negative, which is 8 minus 6 is 2. So dp dt, the change at the perimeter is 2 centimeters per second. So as I let this problem go on for a little bit longer, every single second my perimeter is going to be 2 units bigger. All right, a circle is expanding. Find a relationship for how its area is increasing over time. All right, the area is pi r squared. We can take derivatives. Derivative of a is just dA dt. And here's where people sometimes get confused. Pi is not a number the way we normally see it, but pi is actually a number. Pi is just 3.14. So pi is a constant, so when I do my derivatives, pi stays. Derivative of r squared is 2r. And then because I took the derivative of an r, I do that little chain rule, dr dt. All right, so now if I knew the radius and how the radius was changing, I could figure out how the area is changing over time. Really, this whole video is just kind of get used to doing this. Whenever you're doing these derivatives with respect to time, you're going to have a lot of these things that are d something over dt. All right, so quick summary. All right, you're going to start with an equation that you're kind of focused on. All right, perimeter, area, those are the main things we look at. And then take derivatives. And then that one problem we saw that had values, we'll do more in the next video. But you only plug in values that are changing after the derivative part. Because if you plug them at the beginning, there's no way they could possibly be changing. So you do it after the derivative part. All right, but we'll do more examples with more numbers and scenarios in the next video.